All right, so now we're going to prove the second principle of mathematical induction using the well-ordered principle again. So the second principle basically states, let S be a subset of positive integers and suppose that 1 is an element of S, and whenever 1, 2, 3, all the way to k is an element of S, it follows that k plus 1 must also be an element of S. Then we know S must be the set of positive integers, and of course the equivalence statement here, but just like last time, we're going to prove it in this form, okay? So let's go ahead and start with what this statement is. Just like the first principle of mathematical induction, this second principle is also an if-then statement. So let's identify our hypothesis. So P, our hypothesis is S is a subset of the positive integers where 1 is an element of S and uh, just like last time, 1, 2, 3, dot, 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 k are all elements of S, and this implies that k plus 1 is an element of S. Okay, so this is our hypothesis, right? And then our conclusion, right? So S be a subset of positive integers. We're supposing this and this. It follows this, right? If I have this, then it follows that k plus 1 is an S. And this is the Q part, right? Then, so S is equal to the set of positive integers. So S is equal to the set of positive integers. All right, so just like before, we're going to do the negation of P implies Q is equivalent to P and not Q. So let's go ahead and start our proof by contradiction. Okay, so we're going to suppose P and not Q, right? We're going to suppose that basically all of this stuff and that S is not in S is not the set of positive integers, right? So just like last time, if S is not the whole set of positive integers, then thus there exists T, which is a subset of the positive integers, where S union T is equal to the set of positive integers. T intersection S is equal to the empty set, and T is not empty. Okay, so now since T, by the way we defined it, right, is a subset of the positive integers, and T is not empty, right, by the well-ordering principle, we know that there must exist an N contained in T that is the least element in T. Okay, and of course, from our assumption, since 1 is an element of S, this implies that N must be bigger than 1, right? Since N is an element of T and T is a subset of the positive integers, and 1 is an element of S, 1 being the smallest element or the least element in the set of positive integers, that means this N that's in T must be bigger than 1, right? And of course, just like last time, this implies that 0 is less than n minus 1, right? If we subtract 1 from both sides, n minus 1 is bigger than 0. And of course, this is less than n. Okay? So we have n minus 1 is bigger than 0, and n is a positive integer, right? And 1 is a positive integer, so n minus 1 must be a positive integer, right? So this implies that n minus 1 is an element of the set of positive integers, and where n minus 1 is not an element of T, because n is the least element, so n minus 1, n is the least element of T, so n minus 1 can't be an element of T, right? So if n minus 1 is not in T, the only other place it can be in is S, right? So this implies n minus 1 is an element of S. So we do have that, remember, 1 is an element of S, and all of these are elements of S, right? And for any element that's in S, that element plus 1 must also be in S, right? So this implies that n minus 1 plus 1 is an element of S. And of course, n minus 1 plus 1 is just n. So this means that n is an element of S. Well, we started with n being an element of T and n being an element of S. So this means that S intersection T is not empty. But we know S intersection T must be empty, right? Because that's the way we designed it. Because if S isn't the whole set of positive integers, right? That means there exists a subset T that has everything else, right? So S intersection T is not empty. And this is our contradiction. Okay, thus, the negation of P implies Q, right? What we did here formed a contradiction, so that means this statement is false. Therefore, P implies Q is true. Essentially proving that this second principle of mathematical induction is true.